Good day and welcome to the Moscow Telecommunications Seminar. Our today's speaker is Artem Krasilov. Artem is a senior researcher at the Institute for Information Transmission Problems of the Russian Academy of Sciences and Higher School of Economics. He has been involved in various national and international research projects supported by both academic foundations and industrial partners. He has co-authored over 40 research papers. Today, he will tell us about peculiarities of using TCP protocol in future high-frequency wireless networks. Artem, the floor is yours.
Vyacheslav, thank you for introduction. Dear colleagues, good day. Okay, let me start my presentation. So I think everybody can hear me well. So today we will talk on very interesting topic, and this topic is related to performance of the transport layer protocols in the future wireless networks. So here you can see the short outline of my talk. So first of all, we'll start with introduction to the object. So I will explain you what we mean under high-frequency wireless networks and what are their peculiarities. Also, for those of you who are not very familiar with TCP, I will remind you some key concepts, some key features of the TCP. And then the main part of our talk will be related to the question how well the TCP will work in future networks, what issues arises in these networks, and what are particular solutions we can use to improve performance. And finally, we will conclude our talk with some summary of what solutions are the most promising, what are the implementation issues, and what we can do to improve TCP performance in future networks. So, as all of you know, the key driver of developing new wireless technologies is the request for higher data rates. And if we look to existing cellular technologies like 1, 2, 3, 4G and Wi-Fi, actually all of them are utilizing only small amounts of spectrum which is currently available. In particular, they all work below the 6 GHz. So since this is a very low amount of spectrum, actually the performance, as we know, is limited by the bandwidth, and the maximum bandwidth which is achieved, can be achieved in this band, actually is limited by a few megahertz of the bandwidth. And most of the work were focused on how to provide the efficient transmission, so in order to provide high spectral efficiency. So utilize each hertz more efficiently, and Wi-Fi and cellular systems utilize new modulation coding schemes, MIMO, and other tricky techniques in order to increase spectral efficiency. And what we see that each hertz is used 10 times. So we currently achieve approximately 10 bits per hertz per second. However, this trend goes to saturation, so we are very close to the Shannon limits, and further improvement of the data rates in this band is limited. And one of the promising ways how we go further, how we can improve the data rate, is actually go to higher frequencies. And the next frequency bands after the 6 GHz available for wireless communications is so-called mmWave band, which is between 24 GHz and 100 GHz. And actually, the recent specifications of 5G systems and new amendments to Wi-Fi develop the solutions which work in these bands. So in particular, in 5G, the new radio includes the operation in so-called frequency range 2, which is exactly the mmWave band. And also the Wi-Fi also have .11ad and AY specification, which specify how the Wi-Fi will operate in 60 gigahertz band. And actually the products are appearing in the market, and recently we have news that, for example, our operators run 5G test beds, 5G areas which actually operate in the millimeter wave band, because only the millimeter wave band in Russia is available for deploying 5G currently. And if we talk on the future, so for 6G, the candidate bands will be also a terahertz and lightwave bands, which provide even more bandwidth with the goal to reach hundreds of gigabits per second. So the natural question, however, why only now we utilize millimeter wave bands? Why such an easy solution did not come to reality in the past? And actually, this is connected with specific peculiarities of the wireless links operating at such high frequencies. So first of all, when we go to the millimeter wave band, the first problem arising is the high path loss. So as we know from the Friis equation, the channel, the path loss is inversely proportional to the square of the frequency. So if we go higher to frequencies, the path loss becomes much severe. And to solve this problem, so the solution to solve this problem is to use directional transmission. And then currently, if we look at the devices which operate in the millimeter wave band, they use antenna arrays consisting of many elements, and the idea is to create a very narrow beam and increase the power radiated in some specific direction. However, even with these techniques, the coverage of millimeter wave base station reach only a few hundreds of meters. And for the operators, it's a headache how to deploy, how to obtain continuous millimeter wave coverage. So the only solution is to increase the density of the deployed millimeter wave base station. And the second problem is the high blockage probability. It means that if we put an obstacle between the transmitter and the receiver, the signal will attenuate so high that we even cannot use this path. And the only solution is to use adaptive beamforming. So we redirect our beam to some reflecting surface and obtain some so-called non-line of sight path. And on the right picture, you can see how the capacity of the millimeter wave link changes when the user moves along the trajectory. And you can see that when the user moves behind the obstacle, we see a very sharp decrease of the capacity. And the reason here is that the link transits from the so-called line of sight condition to non-line of sight condition. Then, when the user moves after the obstacle, we can return to the line of sight path, and then we see a significant increase of the data rate. So again, because of this high blockage probabilities, the solution is to adapt our beams to the current conditions and to find the beam which provides the maximum signal strength. And the other solution, for example, introduced in cellular system, is called the multi-connectivity. So if we see that the performance of millimeter wave significantly drops, for example, if we can see at the moment of 20 seconds, we see that the performance of low frequency link in terms of data rate is higher than the red link. So actually, what we can do, we can switch to the blue link, or that is also allowed by the standard. We can use both of the links to transmit the data. So to summarize, so what are the main peculiarities of high frequency links? For example, the millimeter wave links, and actually, if we will talk on the terahertz and lightwave band, actually they will have the same problems, but they will be much more severe. The good news is that the capacity of millimeter wave links definitely can reach several or even tens of gigabit per second. However, the bad news is that this data rate is not stable. So with very high probability, this data rate can instantly change by several orders of magnitude. So it can very fastly reduce and very fastly increase. Let us now turn to the other parts of our talk of the transmission control protocol. So since we're using applications in our wireless networks, to many of the applications like web browsing, file sharing, or social network clients, we need to provide very reliable data delivery and very fast data delivery. And so to provide this opportunity, there is a protocol which is called Transmission Control Protocol, which is responsible for providing this opportunity. So why the TCP is widely used? Because it provides a connection-oriented approach. It provides reliable and in-sequence delivery. And the third and very important part of TCP protocol is to control the load on the network in order to avoid congestion. So it's very important to send appropriate amount of data to avoid packet losses. And the TCP is relatively old protocol. So from the first specification, so the TCP is developed by the Internet Engineering Task Force, and this specification is called Request for Comments. And the first specification was published approximately 40 years ago. So the TCP has 40 years history. And of course, the TCP is not something static. It's changed with time, and hundreds or more requests for comments was also introduced, which introduced some additional components and modification to TCP. Also, what is important, not all RFCs are mandatory. So some of them describe the key functionality, which is mandatory for implementation, while there is a lot of experimental RFCs which provide some solutions to some specific cases. And for those of you who want to make familiar with this modification, I recommend to look at this RFC, which somehow overviews a lot of modifications of TCP, which was developed so far. Also, I want to note that in contrast to TCP, there is also other transport layer protocols which provides reliable data delivery. This is a modern protocol designed by Google called QUIC, and stream control transmission protocol, which is used, for example, in cellular systems to transmit control information between network nodes. So today we will focus particularly on TCP, but however, the solutions which we will describe today will be also applicable to QUIC and TCP. So as I mentioned, the main component of TCP is so-called congestion control algorithm, and this algorithm is responsible on determining how much data the server will send into the network in order to transmit the data to the end user. And if we will consider two devices, two end devices, server and the end users, the path between these devices actually goes over the internet consists of many links. these links can have very different characteristics. However, for the end users, the key performance measures is first the round trip time. So round trip time is the time which is required to send the packet and receive an acknowledgement. So actually, if we look at this link as some tube, this is the length of this tube. Another important measure is the capacity of the bottleneck link. So if we go over different links on the path, we always have a link with the lowest capacity. And actually, this link determines the maximum rate with which we can send the data without causing packet losses. And because of transport layer abstraction, so the server operates at the layer 4, it can only utilize the information available at the server or at the UV site in order to select how much data it can send to the network. And in order to control the loads, the TCP standard keeps a variable called congestion window. So congestion window is the maximum amount of data the TCP sender can inject into the network without obtaining an acknowledgement. So we send some data waiting for the acknowledgement. And the amount of data which can be sent to the network without obtaining an acknowledgement is limited by this value called congestion window. And it can be easily seen that the rate, so the amount of data sent per time unit, is the ratio of congestion window and RTT. If we try to control this congestion window, and if we select the transmission rate higher than the capacity of the bottleneck link, what will happen? We will see that the queue at the bottleneck link will increase because the service rate is lower than the arrival rate. And eventually, since the queue at the bottleneck link is limited, the queue will overflow and packets will be lost, which leads to the problem that the TCP sender will need to retransmit these packets. So actually, this effect is known as congestion. And another situation, if we send with the rate which is lower than the capacity, of course, we underutilize the link, and the performance of the TCP is low. So if we look at this situation, so the main goal of the congestion control algorithm is to keep the congestion window as close as possible to the so-called bandwidth delay product, so the product of the capacity and the round trip time. As I mentioned, so the TCP sender, so server in our case, have no knowledge of the particular characteristics of each link. And it should use some heuristics and somehow control the congestion window. If we look at different congestion control algorithms which is proposed so far, actually there is some standard behavior which is described in RFC 5681, which states that any congestion control algorithm can be divided into 4 main parts, into 4 interconnected algorithms, which is listed on this slide. And this algorithm used depending on how much data we currently send and depending on which signals from the network we obtain. The first algorithm is the slow start. So when we just established the TCP connection, actually we don't know the properties of the network. So what are the maximum sending rate which we can use to send the data? And the approach here is to increase the congestion window until we will see some packet losses. So, and according to slow start algorithm, this is done in exponential manner. So this implements some kind of binary search. So we each round trip time, we try to double congestion window until we see the losses. So at the third point, at this point we see the TCP sender, based on the acknowledgement arriving from the end user, understands that the sending rate is too high, and what it do, it switch to so-called fast retransmit. It makes so-called fast retransmit procedure. So what it do, it reduces congestion window by some value, by multiplying with some parameter which is less than 1, and retransmit the lost packet, which is detects the first lost packet. Actually, because of congestion, several packets may be lost, and the TCP sender turns to the fast recovery procedure. So during this stage, actually the congestion window almost not change, but the goal here is to retransmit lost packets to cover all losses. Then the TCP sender switches to so-called congestion avoidance algorithm, and the goal of this congestion avoidance algorithm is to keep the congestion window as close as possible to the bandwidth delay product, and if losses occur, then again to switch to fast retransmit algorithm. And actually, if we look at different congestion control algorithm proposed so far, so actually the first, third, and the fourth algorithm almost does not change, while a lot of modifications have been proposed for the congestion avoidance algorithm. And the reasons, because if we look at this picture, so most of the time the TCP sender executing the second procedure. And today I will talk more details about how many algorithms have been proposed and how they operate. And currently, one of the widely used algorithms, and we will consider it as a baseline, is called cubic. And the idea of this algorithm is as follows. So we try to increase the congestion window. So the TCP sender tries to increase the congestion window according to some function until the packets are lost. And why the cubic function is selected? Because it has very nice property that it has two regions. So the first region is the flat region, which is close to the inflection point, where the congestion window changes very slowly. So if we determine the bandwidth delay product accurately, we need to keep this inflection point as close as possible to the BDP. However, if some error in estimation of BDP occurs, we need to fastly increase the congestion window to find the new value of 7D. So this is responsible for that. Responsible the other part of the cubic function. So as we may see that the TCP sender, it changes according to some heuristic, it changes the congestion window in order to keep it as close as possible to congestion window. However, we see that this is done in approximately smooth manner, so we do not change very fastly the congestion window. And this brings us to the very important question. So if we see that the high frequency links will behave very interactively, so they will change the performance of the link changes very fast, while the congestion window, according to the existing congestion avoidance algorithm, is changed smoothly, actually, do we have some problems in performance of TCP? And this question raises a hot topic which actually started approximately 5 years ago. And below you see only a small portion of publications on this topic. So actually the list of these publications is 10 times longer. And what people are trying to understand, first of all, they try to understand whether we will have some problems. And the short answer is yes, we have problems. And today I will talk in detail what are these problems. And second, since we have performance issues, we need to solve them somehow. And another question is whether we need some new algorithms. So can we use the existing algorithm which is proposed, for example, by the IETF or research community for the last 40 years? So there is a lot of things that was done about TCP. So actually the question, do we need something new, or maybe we can utilize something existing to solve the new problems? So let us start with the first topic. So let us discuss what are actually problems arise for TCP when we transmit the data using TCP over high frequency links. And the first issue is called the slow start problem. And it's connected with the operation of the initial procedure. So if we return back, so this is the initial procedure. Sorry, when the TCP sender just connects to the network, it uses slow start procedure to increase congestion window. So it's not exactly send the data with the rate available in the network. It somehow changes. And the question, how fastly we can transmit some limited amount of data. If we want to transmit the file of size S over the link with the capacity C, so what we expect is that the time needed to transmit this data is exactly the ratio of the size by the link capacity. So in the bottom figure, this is shown by the red line. However, if we look at the real time, which is needed by TCP to transmit this data, we see that after some capacity, we see a saturation. So the download time does not reduces inversely proportional to the capacity. And the reason for this behavior is exactly the operation of the slow start algorithm. And what is interesting, if we look at high frequency links, which provides gigabits or tens of gigabits per second, this problem becomes much more severe. Also, what's the interesting observation, if we look at the ratio of the download rate and the capacity, we will see that the efficiency of the utilizing the channel becomes very, very small. So actually, when we transmit data, we only 20% of time we utilize the channel. So the second issue is connected with the high fluctuation of the link capacity. So here we can see the example when we have millimeter wave link, and periodically some objects appear between the transmitter and the receiver, which cause the transition from the line of sight to the non-line of sight, and then back from non-line of sight to line of sight condition. So in terms of the capacity, we see the sharp decrease of the capacity, while when the object removes from the link, we see a high increase of the capacity. And actually, when the line of sight or non-line of sight transition occurs, so the capacity drops and the queue at the bottleneck link starts to increase, which leads to packet losses. And what the TCP sender sees the losses, and the reaction to these losses is the reduction of the congestion window. So we see that the congestion window after this transition several times reduces. However, when the opposite situation occurs, so when we transit from the non-line of sight to line of sight, we see that since the existing congestion avoidance algorithms change the window smoothly, this window is not enough to utilize the whole capacity, and we see that we increase the throughput. However, we does not achieve the maximum possible throughput, so we lose throughput. One of the solutions, which is currently by default used in the which is implemented by the wireless device vendors, is to keep high buffer. So actually, if we keep the buffer which is higher than the bandwidth delay product, actually when this transition occurs, we can utilize this buffer to fill up the pipe and to utilize all the capacity. So for example, if we use infinite buffer, we see that we can utilize the whole throughput. However, what happens when we use large buffers is actually a problem that any other application which tries to transmit the packet, they will see very long queue, and this problem is known as the buffer bloat problem. So if two applications, for example, one application which use bulk TCP flow, for example, a video flow or file transmission, and then in parallel you use you want to do a charting or, for example, web browsing, the packets of the second flow will see a very long queue, and you will see that the response times becomes very, very large, and even goes to several seconds. So, and actually this is very bad for the interactive application. The third issue is connected with the multi-connectivity. So as I explained previously, the coverage of the millimeter wave base stations can be very low. And actually, to provide the continuous coverage, sometimes we need to work with the low frequency base station, while when the channel conditions is good, we can use the millimeter wave base station. And actually, the question arises whether we can utilize both of the links. And currently, there is two solutions how we can utilize the multi-connectivity to improve the TCP performance. The first solution is called the multipath TCP. The multipath TCP is extension of the initial TCP protocol to support transmission of the data over several paths. So actually, if we provide two different interfaces with IP address 1 and IP address 2, we can set up two subflows, and the server will manage how much data we will send over the blue path and how much data we will send over the red path. Another solution is to use so-called multi-connectivity approaches at layer 2. And the idea here is that the link layer, so the multi-connectivity is implemented at the link layer, and it is hidden from the TCP sender that there is several paths. So from the TCP layer perspective, this situation looks like a combined tube with some specific characteristics, while the separation of the packets of a single flow occurs at the layer 2. And for example, in the cellular system, there is so-called PDCP protocol, which is responsible for splitting data into several paths, and then to merge this data, so to provide in sequence delivery, and also to look if some data arrives not in time. And if we compare these two approaches, so both of them allow us to utilize more efficiently utilize the bandwidth when we have several connections. However, they're strong, and they have benefits and drawbacks. And if we look at the multipath TCP, So actually, the benefit is that we do not require any interaction between the base stations. So in these cases, these base stations can be independent. So they, for example, it could be a Wi-Fi access point and cellular base station. And for the TCP sender, it doesn't matter whether these 2 points interact or not. However, the drawbacks of a multipath TCP is that it should be supported by both sides. So actually, the multipath TCP is not widely spread, and only several operating systems like Linux and iOS supports the multipath TCP. And in order to expect the widespread of this multipath TCP, it should be implemented and should be supported by both the user and the server. And the second drawback of this approach is that we have very long delays. So if we understand that something happens on the blue link, the time to retransmit the packets is much higher than in the right case. In contrast, so if we talk of the multi-connectivity, so the benefits is that we are compatible with legacy TCP. So in this case, TCP even does not know that we have several paths at the wireless part of our network. Also, the benefit is that we can do load balancing, so balance the load between these 2 paths in more efficient way because we are close to the base station. We know the characteristics of the wireless link, so we can select to split the flow in a more efficient way. And also, if we compare with the previous situation, we have much lower control loops, so we can more efficiently retransmit packets if something happens. However, some also limitation with this technology is, first of all, that is it is technology dependent. So both these devices should be of the same technology, and in particular in cellular system, this multi-connectivity is implemented in one way, while for the Wi-Fi it's implemented in the other way. And of course, there should be interfaces between these 2 devices. That's why we need that these 2 devices should be the devices of the same operator. However, for both of these approaches, the common issue is how to efficiently utilize different paths, which may have different characteristics. So, for example, millimeter wave bands can have high capacity, but high variability and high probability of link outage, while low frequency links, they have stable but low throughput. So the research question is how to efficiently utilize several links having different characteristics. Now we have discussed the issues. Now let us discuss what we can do with these issues. So what solutions can be used to solve these issues. So, and the first natural approach, since the problem are caused by the congestion control algorithm which is used at the TCP server, so the natural question, can we change congestion control algorithms? So can we use more sophisticated algorithms to take into account this variability of the high frequency wireless links? And actually, the development of this congestion control algorithm is a very has very long story, and there is hundreds of CA algorithms proposed over 40 years. And if we talk separately about slow start and congestion avoidance, so there is some slow start modifications. So the initial stage of the congestion control, but actually this modification is related to the problem to avoid massive packet losses when the congestion window reaches bandwidth delay product. So actually, in high BDP networks, there is a problem when we reach the BDP, and with high probability, we can overshoot this BDP, and this will lead to massive packet losses. And so the idea of all this solution is to slow down the TCP when it's close to the BDP. However, if we look from the point of the slow start problem, this solution do not speed up slow start, they slow down, and thus they do not solve the slow start problem. So actually, in existing solutions, we have not seen any efficient solutions for the slow start problem. If we talk on the congestion avoidance algorithms, so again, there is a wide variety of different algorithms, and so these algorithms can be classified into different groups depending on which design principles are put inside these algorithms. And so the historical first group of CA algorithm which have been proposed in the research community is so-called loss-based algorithm. So the idea of this algorithm is very simple. So we try to gradually increase congestion window according to some law. For example, in URINA, we use a just linear law. In cubic algorithm, we use a cubic function. And if we detect the packet losses, we reduce the congestion window and then start to increase it again. So there is a lot of algorithms that was proposed so far, and I would like to pay your attention to first the so-called URINA algorithm, which is the algorithm used in the 18th or 19th. It was the default algorithm used in most of the systems, and it was a standard algorithm until the high-speed networks occur. And this algorithm was replaced with cubic because the URINA is not enough to utilize high-speed links. If we look at the drawbacks of this approach, is actually the drawback of loss-based algorithms is that they create long queues. So since they reduce congestion window only when the packet are lost, typically this happens when the queue overflows. So all of these algorithms tend to create a very long queues and utilize all the queue until the packets are lost. The opposite idea to that is so-called delay-based algorithm, and the example of this algorithm is Vegas and its numerous modifications. So the idea here is to again increase the congestion window, but reduce the congestion window when the round-trip time significantly increases. So if we see that the queue at the bottleneck link increases, this will be seen by the increase of the round-trip time. It means that we reach the bandwidth delay product, and we need to reduce the congestion window. However, even these algorithms have a very nice properties, so they provide a very low delay. However, they are too conservative with respect to loss-based algorithms. So the story was the follows: the loss-based algorithm was introduced first. So, for example, URINA was introduced earlier than Vegas, and since it was already used in the servers, the researchers have tried to simulate the operation of URINA and Vegas, and found that the following thing, that the loss-based algorithm, they are more aggressive, so they utilize the bandwidth and does not care about the curing delay. While the Vegas will back off, and that's why the URINA will utilize will obtain all the capacity, while Vegas will obtain zero capacity. That's why this algorithm have not found widespread. However, these nice properties is promising and is good for the application which work in background. So, for example, the delay-based algorithm currently, the algorithm called LedBot is used, for example, for software updates and BitTorrent applications. The third group of algorithms tries to actually combine the benefits of loss-based and delay-based algorithm, and the most widely known example of such an algorithm is the compound TCP. So actually, this algorithm was used in the oldest version of Windows. So currently, according to our knowledge, starting from Windows 10, the Windows also uses cubic as the default congestion control algorithm. However, these hybrid algorithms also have some issues, and that's why they did not find also a widespread over the devices. Another approach, which is called capacity-based algorithms, is based on the following idea. So since the optimal congestion window should be selected as the product of the capacity and RTT, so let us try to estimate these two values. For example, the RTT can be easily estimated based on the time difference between transmitting a packet and receiving an acknowledgement. However, the capacity, so to measure the capacity, some more tricky algorithms needed, and some of them was proposed in Westfoot, and another proposal, which is the modern congestion control algorithm proposed by Google. It is called BBR, and also it also uses some technique in order to estimate the capacity and then set the congestion window to the product of capacity and RTT. However, the research on these congestion algorithms show that they have not so good performance, especially in wireless links, because they have high errors in estimating the capacity. For example, when the user moves with high speed, or in future when we will use high frequency links. A new generation of the congestion control algorithm, which is developed recently. This group of algorithms is called machine learning based algorithms, and here the idea is that we can look at the selection of the congestion window as some learning process. So we can select some congestion window, we will see the acknowledgements arriving, we will see the packet losses, and the idea is to use some machine learning approach to select this congestion window. However, these machine learning algorithms, currently they are still at the infancy, so they only proposed by some researchers, they tested by simulation. However, we didn't see currently the large scale and real life validation, so how they will work over very different internet links. So the research on this algorithm still continues. And as I mentioned, there is more and more algorithms developed every year, and the natural question, so whether this development will stop. And actually, I very much like this comics about development of BBR. So the developers of BBR in Google, they stated a very ambitious goal to provide the congestion algorithm which actually the best in all the cases. However, after the years of the research of BBR, it was understood that actually, yes, BBR works well in some scenarios. It allows to reduce the delays. In some cases, it performs better than cubic, but it's not the best solution in all the cases. And actually, my understanding why this story continues, because most of the algorithms, they are based on some heuristics. So they use inside this algorithm, they use some assumptions, some heuristics, how to tune the congestion window. And because of high heterogeneity of internet links, so we have wired, wireless, satellite links, which have very different characteristics, and the capacity and round trip time significantly differ. So my understanding and many other researchers also state that it's difficult to develop the solution that one fits all. So, and I think this research will continue, but whether we will have the winner, let's see. So yeah, the research on this area still continues. From our side, we have also done the experiments with different congestion control algorithms in NS3. So in NS3, there is implementation of the different congestion control algorithms. And actually, what we see that the same conclusion is that there is no clear leader which provides both high throughput and low delay. So the loss-based algorithm, as I mentioned, they tend to provide high throughput. However, they suffer from the buffer bloat problem. In contrast, delay-based algorithms, they provide low delay. However, they suffer from throughput problem. So from the perspective of the selecting the congestion avoidance algorithm, so there is no unique solution which provides the best performance in all the situations. So in this area, so the status quo is that we still can use cubic, but we will suffer from buffer bloat problem. But actually, in the next slide, I will show you how we can bust the buffer bloat problem even if we use the cubic. So let me look at in the charts. Maybe we have some questions. So the question from Mikhail Lubogoshev for the independent path case, what about the routing for MPTCP? How the packets learn about the second path? Does the MPTCP require some support from the network? So from the network network perspective, so if we return back to the multi-path TCP, so actually the idea how we can set up several paths is that we create two different IP addresses, and actually the route is found as the route from the server to this IP interface, and it is done by usual existing routing protocols. So when we connect to these two different networks, the only thing we need to do is to provide two different IP addresses for the one interface which is connected to low frequency base and another interface connected to the mmWave base station. And of course, we need to support of a multi-path TCP functionality at both sides, at the server and the user. So no other support from the operator side to this solution is needed. Okay, so no other questions. So let us go further. Previously, we have understood that actually the main problem which the server trying to solve is actually trying to understand what is the capacity of the bottleneck link. And previously, we have seen that there is a lot of tricky algorithms which try to find this according to some laws. But the question, if we can know this capacity, so actually, can we help the server to select the congestion window? And in case of wireless networks, so typically the last hop, which is the wireless link, actually, if the network is designed properly, actually the wireless link is the bottleneck. So if we have an opportunity to measure the capacity of the link at the base station and somehow to share this information with the server, so we can assist, we can help the server to select the proper sending rate. Actually, there is proposed a lot of solutions how to provide this cross-layer information. And so from the network side, we can provide such measures like capacity or buffer size. So if we see that the buffer increases, we can say, for example, server, please slow down the sending rate because my buffer increases. On the other side, the server can notify the user, the network on how many data it wants to transmit, which is the quality of service requirements. For example, if it is background flow, for example, we can suspend transmission of the background flow. So let us consider what approaches can be used to exchange the cross-layer information between the transport layer and the link layer. So the first idea, which is considered in literature, is called the in-device interaction. So the idea here is if the TCP sender is located in the same devices which operate on the wireless link, so this information can be easily exchanged between the layer 2 and layer 4. So, for example, this can be used, for example, for the uplink transmission. So in this case, the user device becomes a TCP sender. And since the user device operates in the wireless network, it can measure the channel quality and then to assist the selection of the congestion window. However, again, this solution have limited application because we require that both layer 2 and layer 4 implemented on the same device. Another approach which is available in the TCP protocol itself is to put the cross-layer information in the special header field. And in particular, the TCP provides some special field which is called TCP options. And this is a container in which some devices, in particular, it could be end devices and also some intermediate devices, they can put some information. And the examples of the solution which is based on the usage of TCP option field is explicit congestion notification. So this solution allows the intermediate device to notify the sender about the congestion, so without dropping the packet. Exactly. Another interesting solution, which is called Quick Start. Actually, this solution is provides the information to the server about the link capacity. So how it works? So the server sends a special TCP option field in which it requests the minimal capacity of the link. If intermediate devices support this option, they put exact values inside this TCP option and then traverse it over the direct and the reverse paths. We can determine the minimal value of the capacity and then use this, for example, for selecting the congestion window. However, these approaches have two main problems. The first problem is that not all devices support these fields and options. So in particular, to implement Quick Start, we expect that all the devices will support this option and will put reliable information to this option. Another bad thing, which is actually occurs in the network, that some firewalls and some they're called middle boxes, they can cut off unrecognized options, and this is a really headache for the TCP developers because some options are very important for the good TCP operation. However, these bad middle boxes, they just cut off it from the TCP packets. And the third approach is to actually provide this information using some specific protocol, some service protocol. And the example of such a protocol was developed in the joint project with Huawei. This protocol is called Extreme, and the idea here is as follows. So if we have a data connection between the client and the server, we can set up additional connections. For example, it can be other TCP connection between the server and the network. For example, it could be G-Node or some other device inside the network. And using this control connection, we, for example, can transmit the current estimation of the link capacity at the base station. So the only implementation issue of this approach is that this solution actually should be supported by both sides, the network operator and the server provider. So, for example, if this is a Google, it also should support Extreme, which is not so easy in terms of implementation. However, if we look at the results which can be achieved with this cross-layer interaction, we can see that we can significantly increase the performance of TCP. And here we show the result again in the mmWave network. So we see that the download rate reaches several gigabit per second. And especially when the round trip time between the server and the user is high, we can reach even several times increase of the download rate. So usage of this cross-layer interaction is a good solution to which efficiently solves the slow start problem. Also, this solution can be efficient when the channel capacity changes very fast. So we can use this control connection to notify the server to reduce the sending rate, for example, when the capacity of the link drops. Another type of solutions which I want to discuss with you is the solutions reducing RTT. So actually, the performance of the TCP, so how fastly the server selects the congestion window, how fastly it can change, it actually depends on the delay which is experienced by the packets over the network. And if you can consider example of the cellular network, we can see that this RTT can be divided into three main parts. The first part is the path between the server and the gateway to the cellular system. The second part is the delay inside the core network of the operator, and the third part is the wireless link over which we transmit the data. So, and currently there exists solutions which try to minimize, to reduce this RTT on different parts of the network. In particular, from the service provider perspective, so the idea is to put so-called replica servers close to the user, and this approach is called content delivery networks. So, for example, if we have a Google, it puts server not only in the United States, it puts its servers in the Europe, Russia, and etc., in order to reduce this latency between the server and the user. From the network perspective, currently the 5G specification utilizes the idea which is called network function virtualization. So if previously the packet gateway was some specific device which had some specific geographic position, in 5G systems, the packet gateway is some network function which can be implemented in software and actually can be executed at any node which provides sufficient computing resources. For example, if at the base station we have sufficient computing resource, we can even reach zero delay between the packet gateway and the base station. And the third part actually the novel technologies allows us also to improve the delay in the wireless link. And in particular, in one of the papers, we have shown that actually by proper selecting the duration of the transmission times for the base station, we can speed up slow start process and efficiently increase the data download rate using the flexible slot allocation in the cellular system. So let us see what are the benefits. So why we need this low RTT. So if we look at the bandwidth delay product, so if we reduce the round trip time, we require the congestion window to reach BDP. So if we use low round trip time, we can faster reach the BDP. And you can see on the left plot that, for example, reducing RTT from 30 milliseconds down to 1 millisecond allows us by one order of magnitude reduce the file download time. Also, if we have the lower RTT, actually this is good in the sense of selecting the congestion window by the existing congestion control algorithm because we faster react to the congestion events or to some other events. So if we look here, we see that selecting RTT of 5 milliseconds allows us to faster react to the changes of the link capacity. Okay, maybe we have some questions in the chat. Can a 5G virtualization concept help with in-device interaction, be closer to the TCP server? So if I correctly understand the question, so actually if we can execute server functions in somewhere other devices, so for example inside the operator's core network we can execute the server the storage and computing functions of the service provider. So we can provide them virtualized resources and provide computing resources. So actually, yes, we can, in the same manner, we can move virtually, we can move the server close to the base station, and thus we can reduce round trip time. So it's also a good approach to help TCP to operate better. Okay, we also have two other topics. So one of the approaches which is currently considered in the research community is the usage of so-called performance enhancing proxies. So what are these performance enhancing proxies? So performance enhancing proxies is some logical nodes which can be put on the path between the server and the user, and the idea of and the goal of this node is to somehow try to help server to better utilize some link between the server and the user. In particular, if we talk on the wireless system, so the better approach is to set the performance enhancing proxies close to the base station. And actually, the performance enhancing proxies is not a new idea. So actually, this performance enhancing proxies was developed 20 or 30 years ago. In particular, they found a wide adaptation, in particular in satellite systems, because in satellite system there is some specific properties of the wireless link, and there was proposed a lot of performance enhancing proxies for the satellite link. Now we see that in literature there is other proposals of performance enhancing proxies specifically for the 5G systems, and according to these RFC, so we can differentiate two types of performance enhancing proxies. The first type is called split performance enhancing proxies. So what the idea of this approach is that we divide the initial connection into two connections. So one from the server to the performance proxy, another from the PEP to the user. So, and actually this can be implemented transparently to the user. So the user will even don't know that there is some split in the middle. So what this PEP do? This PEP use like a user for the server. So it tries to download the data from the server, and it can by itself send acknowledgements which acknowledge the delivery of the data. It buffers this data and then use the second connection to deliver this data to the user. So what are the benefits of this approach? So first of all, it reduces round trip time. So for the second connection, we have only part of the RTT which is needed to be traversed. And the second benefit is that at the second connection, since we are a server in this case, we can use its own congestion control algorithms, and in particular, if we have cross-layer information from the base station, we can appropriately select congestion window. So even if server implements other congestion algorithm like cubic, we can set up a performance enhancing proxy and change the and select the congestion algorithm which we like. Another type of performance enhancing proxies is, sorry, let me go back. So there is one very huge drawback of the split PEP approach, which is reported by the researchers, is actually that it breaks the end-to-end semantics of TCP. What does it mean? So actually, when the server sends the data, it receives acknowledgement. And since the TCP provides reliable data delivery, so if we receive acknowledgement, we expect that the data is delivered to the user. However, in this situation, actually, we can be sure only that the data is delivered to the performance enhancing proxy. And actually, if this second connection breaks, we cannot deliver the data from the performance enhancing proxy to the user. And that's why the server will be misled to the understanding that the data delivered or not. However, some people that's advocating use the split PEP, saying that there is a responsibility of the application layer to also provide the application layer acknowledgement. Okay, so another type of performance enhancing proxies is called transparent PEPs. So in this case, we do not break the TCP connection. However, we can do something with packet which traverse this performance enhancing proxy. For example, if we see that the link between the base station and the user, the quality drops, we, for example, can buffer the packets and reduce the amount of data which is sent to the user. When the link becomes better, we can dispatch the packets with higher rate. So the benefits, again, that we don't break the TCP connection. We can change the loads by buffering or dispatching the packet. And also there is a solution which, for example, if we see that the buffer at the performance enhancing proxy permanently increases, we can notify the server to reduce its load, for example, by modifying the TCP receiver field. But the drawback is the additional packets processing delay. So if we look at the performance of, for example, split PEP approaches, we see that they provide some benefits. However, this benefit is much lower than to have a cross-layer information. Okay, so let us now move to the other type of solution. So As we've seen, the buffer bloat problem, which occurs at the bottleneck link, is actually occurs because we are not efficiently manage the queues. And the simplest queue management algorithm which is used, which can be used at the device, is just keeping some buffer. The process the packets according to FIFO principle, so the packets is served according to the arrival order, and since we have limited size, the packets which arrive at the end of the queue, they will be dropped. So the policy is also called tail drop. However, it was shown that this passive queue management is not efficient for TCP, and the researchers have proposed more efficient queue management algorithms, and they called active. So these solutions are called active queue management. So what this type of solution do? They try to efficiently manage queue at the transmitting device. So current active queue management can be classified into single queue active queue management algorithm and multi-queue. So we can keep one or several queues to keep the packets. And every active queue management shall determine three main functions. So it determines a dropping function, so when and which we will drop packets, classification function, in which queue we should put the packet, and the scheduling function. So if we have several queues, the question is how we will serve packets from different queues. So if we talk on the single queue AQM algorithms, they need to determine the only dropping function, and with respect to TCP, the most widely known and used the active queue management algorithm is random early detection and CODL. So they are based on the following idea. So we need to notify the TCP sender that the queue becomes full before it is actually full. And random early detection do it in this following way. It drop the packet with some probability that depends on the current queue size. So the higher the queue size, the higher the drop-in probability. The controlled delay management, which is short name CODL, it actually uses the packet delay as the congestion signal. So if it sees that the queuing delay increases, it drops the packets and it signals to the TCP sender to reduce sending rate and to reduce the queuing delay. Also, there is proposed a lot of modifications of RED and other algorithms which is currently studied, but these two algorithms are most known, most widely studied, and actually implemented in Linux kernels. The modern algorithms uses a multi-queue approach. So the idea here is to create several queues, and each of these queues can be managed according to some dropping function like tail drop, red, CODL, and etc. And the question which and the functions which determine performance of these two AQM algorithms is how we split the packets in the queues and how we serve these queues. So for the classification, actually two main approaches is used. One of this is called clusterful approach. So the idea here is to create several queues and determine the queue based on the traffic class. So, for example, in the IP header, we have some type of service field based on which we can determine whether it is important or less important packet. While in opposite classless approach, so it considers that all the flows have equal priority, and the idea here is to just separate equally the packets between different queues. And in the best case, we can put each TCP flow in one queue. Then, when we have several queues and we transmit the data from these queues, the question is how we serve these queues. And three main approaches is used. One of them is called fair queuing. So fair queuing is just an approach which provides the same service rate to each queue. So, and typically it is implemented as the round robin algorithm. And the idea that each queue obtained the same fraction of the link capacity. In opposite, strict priority queuing, which is typically used with classful approach. So if we have more urgent traffic, we first serve this queue and then just go to the queues with the low priority. And some intermediate solution is called weighted fair queuing. It means that we provide some portion of the link capacity to each queue. And for example, currently the modern algorithms is one of the examples is called FQ-Codel. So what it do, this algorithm uses classless approach. So it creates a lot of queues such that the condition that one flow puts into one queue typically happens, and we just serve the queues in the round-robin fashion. So if we look at the performance of different AQM algorithms, we can see the following results. So first of all, if we consider single queue AQM algorithms, again, if we select too low buffer, we see the low queuing delay. However, we suffer from low throughputs because we cannot utilize the capacity when the non-line of sight to line of sight transition occurs. In contrast, having high buffers leads to the high queuing delay and buffer bloat problem. The active queue management like RET and Codel tries, so they drop packets earlier, they provide low queuing delay. However, they also suffer from the low throughput performance. While if we look at the multi-queue algorithm, so we can see that, for example, FQ tail drop with enough buffer size provides us both the low delay and also high throughput. So multi-queue AQM algorithm could be an efficient way of solving the buffer bloat problem without need of changing the congestion control algorithm. So let me finish my talk with actually providing an answer to the question which is in the title of my talk. So how to make TCP fast. So analyzing different solutions, we can state the following recommendation to different parties like operators and service providers. So the first recommendation is to bring the server as close as possible to the end user, so to reduce RTT. And so from the service provider's perspective, this problem is solved by deploying more and more replica servers, so to enhancing their content delivery networks. From the network operators, so this problem can be solved by also providing computing and storage infrastructure, in which, for example, the service providers can deploy their virtual servers. So there could be a beneficial interaction between the server provider and network operators. And actually, we see that many network operators currently, they provide CDN resources to some service providers. If we talk on the cellular systems, in order to reduce the delays inside the core network, we can use network function virtualization approach and execute network functions again as close as possible to the base station. One of the solutions could be split PEP approach, but I marked it with the gray color because it has some clear problems. The second point is that we see that if we can provide the cross-layer interaction between the server and the network, so based on this information, we can assist the selection of congestion window. And in particular, we see that we can efficiently solve the slow start problem and significantly increase the data download rate in high-speed wireless networks. The third point is about solving the buffer bloat problem. So actually, the buffer bloat problem occurs when we try to mix in the same queue the bulk flow. So for example, if we watch the video and if we do a web surfing, so if we put them in the same queue, definitely we will see the buffer bloat that we have very high delay between sending a request and obtaining the response. So, and actually the modern multi-queue AQM algorithms can be a solution to this problem. So what we need to do, we need to select the queue size higher than the maximum expected BDP. So we need to have enough space in the buffer to catch the transition from the low capacity to high capacity. And also, if we want to minimize the buffer bloat, we need to keep separate queues for the bulk and interactive TCP flows. If the solutions stated above is not applicable, also it could be beneficial to use some kind of transparent performance enhancing proxies. So we can install this proxy inside the operator's core network. In this network, we have an access to the characteristic of the wireless link, and that's why we can again assist the selection of the sending rate on the performance enhancing proxy. So that's all from my side. Let me look the questions in the chat.
Artem, thank you for your presentation. My question is, you already mentioned that, my question is about congestion control algorithms. And as you mentioned, there is no one-size-fits-all solution. But maybe in some literature do we have some mixed approaches? For example, when server dynamically changes different congestion control algorithms, if it detects some situation, it detects some situation in which it understands that the current congestion control which is used now is bad, and move to some other congestion control.
Okay, thank you for this interesting question. So actually switching from one congestion control to another could be possible if the server first implements this algorithm. So actually the TCP is implemented in the operating system. So actually, first of all, this operating system should support these different congestion control algorithms, and in particular in Linux, yes, we have a lot of implementation of different algorithms, and actually for each connection we can select this congestion algorithm. However, the key question, as you mentioned, is to decide when to use one approach, when to use another approach. And actually, if we don't have some assisting information, so if we don't have some information that this link goes over the wireless link and other links, so the server does not know from which network the clients appear. And that's why it's difficult for the server when the client first time connects to the server to understand what will be the best solution. So the answer to your question that is it possible? Yes, it is possible, but it's not clear how to organize this selection, especially in case when the user only once connects to the server. So we need to track from which network the user connects, which the properties of this network.
Okay, thank you.
Okay, the question in the chat from the Ruslan Yusupov: can we use the machine learning approach to classify the network and determine the best? Yes, I think it could be used. So I did not found in the literature such approaches, but yeah, it could be an approach to dynamically select a congestion control algorithm. And also, as I mentioned, from the machine learning perspective, currently there is a huge interest in the research community to develop even machine learning based algorithms. So the algorithm which itself learns from the network how to tune congestion window. Okay.
So I guess that's all. Thank you, Artem, once again for your interesting and very informative presentation. And thank you all the participants for listening. See you next week. The next seminar will be about a new amendment for Wi-Fi standard, which allows Wi-Fi networks to use visible light for communications. So thank you. Bye-bye.
Thank you all for the questions and discussion. Thank you.